All right, chapter 3.3 is the derivative of trig functions. Now we're going to start finding the derivative of trig functions. We're going to start with the derivative of sine x. We're plugged it in. I already plugged it in here into the limit definition, and now we're just going to simplify. Now this does require some trig review. As you can see on the right hand side of the page, I did write those trig reviews equations down. So that's sine of x plus h, remember we can expand into sine of x cosine h plus cosine x sine of h, right? We're going to bring the other one down, minus sine x all over h. Now, in this case, when I take a look at this, I obviously can't just plug in 0 in for h. So I'm going to see how I can simplify this. Well, looking at this, I see that there's a sine x here and a sine x here. So I'm going to try to factor out that sine x from the first and third term. So if I have a sine x left on the inside, I'm left with cosine h minus the 1, right? And then, of course, I have this middle term here, cosine x sine h. And this is all over the term h. I'm going to split it into this term h over this term h, though. Because if you could take a look, we have two terms right now. And right here, we want the limit as h approaches 0 of all of this, right? Now, looking ahead, in planning to simplify, the limit as h approaches 0 of sine h over h, if you can be reminded of the graph that is on the right-hand side of this web page, you can see that the limit as h approaches 0 of sine h over h is 1. The limit as h approaches 0 of cosine h minus 1 over h is 0. And this sine x and this cosine x, well, I'm actually just squeezing h down to 0. There is no variable h in this term, in this function right here. So I can actually pull out the sine x because it doesn't have any h's in there that I'm varying. And then this is what I will have left for this first term. In the second term, this cosine x is what I'm also pulling out because it has nothing to do with the limit as h approaches 0. And I'm only left with the limit as h approaches 0 of sine h over h. Now, in this case, once again, if you take a look to the right, this term right here and this term right here are a couple of famous limits here, where the limit as h approaches 0 of this cosine h minus 1 over h is going to be 0. And the limit as h approaches 0 of sine h over h is going to be 1. So the derivative of sine x happens to be cosine x. Now let's take a look at what that means graphically, right? So here at the very top we have the derivative of sine x, right? Our original function. Our derivative is looking for the slope of the tangent line at any given point. So at this point 0, the slope of the tangent line, we're saying, is the same thing as the output of the cosine. Slope of the tangent line here is 1, this output right here. The slope right here at pi over 2 is 0, right? Because it plateaus right there. And as you can take a look, cosine of pi over 2 is 0. The slope here is going to be negative 1 at pi because the output of the cosine function is negative 1 as well. Okay, now moving on. So we've just done the sine x, cosine x. These are all our trig functions, the 6 main trig functions: sine x, cosine x, tangent x, cosecant. Sine x, cosine x, we also have tangent x as a review, is sine x over cosine x. It is the same thing. Cosecant x is 1 over sine x. Secant x is 1 over cosine x. Cotangent x is cosine x over sine x. We prove that the derivative of sine x is equal to cosine x. You can also prove in the exact same manner that the derivative of cosine x is negative sine x. The rest is just a usage of the quotient rule. Quotient rule, quotient rule, quotient rule, once you know those first two derivatives. Now here is the summary of each derivative once you work it all out. A couple of your homework problems will be to work out the proof, so here it is for now. Derivative of tangent x, once you prove it and simplify using the quotient rule, will simplify to be secant squared x, and so forth and so forth. And this is a copy in your textbook, and it will be in your notes. So now let's move on to the first example. Example 1. For what values of x does f of x equal secant x over 1 plus tangent x have a horizontal tangent? Now, horizontal tangents, what are they asking? Horizontal tangent lines only happen when the slope is equal to 0. So if the slope is equal to 0, we are also looking for when f prime of x equals to 0, the derivative. So let's try finding the derivative of f prime of x. Sorry, the derivative f prime of x. Now, what we can do here, obviously, since we already know the secant derivative formula as well as the derivative of tangent x, we could go straight into using the quotient rule here. However, what I'm going to do is, taking a look, I can see that this right here is 1 over cosine, this is sine over cosine. I can probably get those cosines to cancel. So for me, it's actually easier, and you can go straight into the derivative from here. For me, it's a little bit easier to simplify this function, sine x over cosine x. So I'm going to simplify this function into this. Now, from what I can see, this cosine, this will become cosine x over cosine x, same thing as 1, right? And then this cosine will cancel. So then I'm going to be left with a simplified version, 1 over cosine x plus sine x. From here, I can actually find that derivative. So from here, I'm going to use the quotient rule. It's going to be the bottom times the derivative of the top, which is 0. Right, so I'm just going to write it out. Bottom times the derivative of the top minus the top times the derivative of the bottom, which is negative sine x plus cosine x, all over the bottom squared. All over the bottom squared. Now simplified, that gives me that negative 1. I'm going to distribute in positive sine x minus cosine x all over cosine x plus sine x, the whole thing squared. Right? Now again, what I'm looking for when we were up here, I'm looking for when the slope of the function is 0. Looking for when it plateaus. So then in this case, I'm going to set this slope equal to 0 and see for what values of x does that equal 0. Now this fraction right here can only equal 0 when the numerator is equal to 0. So when sine of x minus cosine x equals 0, as long as that value of x doesn't make the denominator 0. So when does sine x equal to cosine x? Well, if you remember from our trig unit circle, going all the way around, here's 1, 0, 0, 1, negative 1, 0, 0, negative 1. Right here, at square root of 2 over 2, we have the same values. Square root of 2 is where sine and cosine are the same. And then down here, negative square root of 2 over 2 over negative square root of 2 over 2. That's also where it's the same. So it looks like the values of x that make sine and cosine both the same are at pi over 4, 5 pi over 4, and I got to spin it around, plus pi, plus pi, plus pi, plus pi. So after adding every pi. Okay, better way to write that would be pi over, oops, would be pi over 4 plus n pi. Right? So those are the values of x that have horizontal tangents. Moving on to the next example. What if the limit as x approaches 0 of sine of 7x over 4x? We're just going to do a brief u substitution, introduction to u substitutions here for the first time. Now, in this case, this seems to look really similar to sine x over x, but it's sine of 7x, and I don't have any shortcut expansions to that I can rewrite. So what I'm going to do here is I'm actually going to take it one more step and make it look a little more similar to sine of 7x over 7x. And you'll see why in just a little bit. So I need a 7 times x on the bottom, but I can't change that number. So I'm going to multiply 7 to the bottom, so I get sine of 7x times sine of 7x, a 7 over 7, which is just a 1. See how I'm going to rearrange it? I'm going to say the limit as x approaches 0 of sine of 7x over this 7, x, this 7 and this x, and I'm going to be left with a coefficient of 7/4. Now from here, obviously that 7/4 I can factor out, and I'm left with the limit as x approaches 0, 7 sine of 7x over 7x. Now in this case, here is where I'm going to do our first u substitution, where I'm going to call u 7x. So anytime I see a u as a 7, anytime I see a 7x, I'm going to replace it with u. Okay? So in this case, I get 7/4 limit of sine of u over u. And then because my variables are now in terms of u, I'm going to make it so that u approaches 0. Because I replaced the x with u. Now, if I show the work, what is x the same thing as? X is the same thing as u over 7, but I'm shrinking that u 1/7 of u down to 0 anyways. So in this case, I can just do a straight replacement. Now, if from here, if you can tell, I get 7 over 4. Limit as u approaches 0 sine u over u is just 1. So my limit is just 7/4. Right? Now that is the end of the examples for today. When you come into class tomorrow, please make sure that you know your unit circle. Your unit circle. Whoa. Know all of your inputs, outputs, your sine, cosines. If I gave you sine of cosine, what the pi over 4, pi over 6, where all of those belong, the entire circle. Be ready for that by tomorrow. That's it. Bye.